see. Oh, sort of working.
Very dramatic. Okay. Oh, there we go.
Yeah, all right. Okay. Hello, everyone. My name is Jonathan Williams, and I am, as I said, a professor at the University of Hawaii at Manoa, which is over in Honolulu. And I was tasked with giving the Intro to Radio Astronomy start to the course. So this is, and I wasn't sure, I looked at the participant list, and I know there's a wide range of expertise. Some of you have used the SMA or other interferometers, others have not, and I don't know the level of background to an intro radio astronomy. So I've aimed this at a fairly low level, but this works. And it's going to be a short lecture, so you know, it's hopefully I don't, the advanced people don't get too bored. If you are, then you can download this book, because we're basing a lot of the work on this book. This is a open source book. You can actually just Google it or go to this link and type it all in, and you can get it. You can download it as a PDF right now. Another really good book. Let's see if this thing works. All right. This thing works? Oh, okay. So my pointer works on the screen. This is the problem with Zoom. My pointer works on the screen, but not on the Zoom. So anyway, the other good book here is this one by Condon and Ransom. But as I say, I'm going to be giving a very brief and introductory review. Please ask me questions, interrupt me if you want to know more. And of course, we've got a whole couple of days. We're going to hear from all the experts in all the various areas I'm going to talk about. All right, so let's kick it off by just sort of talking. It's very slow. Yes. Thanks. Okay. Okay, good. So slow response, a big lag. All right, so the radio window. Okay, so our atmosphere absorbs most of the electromagnetic spectrum, but there's a couple of windows where light goes all the way to the ground. One is, of course, in the optical, where we can see, where evolution kind of made us work that way to adapt to the atmosphere. And then the other way, of course, is in the radio. And it's this very large window, several decades in wavelength. And so you can build telescopes right on the ground and work from there. And so, in fact, working on the centimeter wavelengths and longer, this work was pioneered in places that are not known for clear skies. So New Jersey, Illinois, England, Holland, right? These are not exactly high. They're fairly low, they're fairly cloudy, a bit like Hilo, really, and that you can still observe at centimeter wavelengths. So the radio regime is broken up into these parts, centimeters and millimeters, and then pushing, just as the technology advanced, we pushed to shorter and shorter wavelengths. And there's lots of reasons to do that, as I'll show later on. And then even what some people are pushing now into the terahertz regime. But it was all pioneered, as I say, in these places, in this regime. And the technology, the receivers and the antennas and so on, to a large extent, borrow on the technologies advanced and the detection methods that were created in that centimeter regime. Primarily, because we're looking at very low energy radiation, it can be treated more, it behaves more like a wave than as a particle. So we don't measure the energy so much. That's possible in the submillimeter regime with bolometers, but we measure more the electric field. So we look at the response of antennas to the passing radiation as an electric field. So we're not measuring the energy, we're measuring amplitude and phase. And that's really important for interferometry, as you'll see throughout this course. Okay, so you'd notice there that I talked about the radio regime extending all the way into actually like 300 microns or so, terahertz. The SMA works right here, and it looks like it's pretty much opaque there. But if you go away from England and Holland and so on, you can go to a high site like Mauna Kea, then you get some partial transparency. So what's plotted here? This is from the SMA the correlator setup. This is now frequency. So it's a little bit different from here. This is wavelength, this is frequency, this is transmission, and this is opacity. But you get the picture that the atmosphere actually is fairly transparent at the level of 80 to 90% in the millimeter, 200 to 300 gigahertz regime. And then there are some big parts where, relatively small parts where it becomes very opaque. And these are due to water and oxygen lines. Simon Radford will talk to you more about that later on this morning. And then, of course, we can also push out into the submillimeter beyond 300 gigahertz. Out here, the transparency is going down, but it's still possible to work there, and even beyond into the 400 gigahertz regime when you have good dry weather. So you want to get dry, you want to avoid the water. The point also is that because these are atmospheric species and they're moving around with the wind and the weather and so on, then the transparency is variable both spatially and temporally. So this will come into play when you consider calibration techniques. Okay, so we're here down in Hilo, where you can see it's beautiful and clear and dry. But we're up in Mauna Kea, right? This is where they build the telescopes up in Mauna Kea because we want to get above much of that stuff. So this is the best site for submillimeter observations in the northern hemisphere. Of course, in the south we've got ALMA, but we're here to talk about SMA. And submillimeter astronomy was pioneered on this mountaintop with the Caltech Submillimetre Observatory, James Clerk Maxwell Telescope. This photo was taken as the SMA building was being built, but before the antennas were out on the site there. Okay, so here's a close-up of all of these. JCMT is a 15-meter telescope. CSO was a 10-meter telescope. It's no longer, sadly. This is a great teaching telescope. It's a great telescope for science. It's a really great telescope for teaching because you could take students up there and you would play around with the really, you could see the whole light path going through. You'd stick a vein in, you'd dip it into liquid nitrogen, stick it in to calibrate, and you would tune it, and you'd be crawling underneath the telescope to move the tertiary mirror around. It was a really good way to see how things are working. But now with the SMA, so hopefully you'll do somewhat similar things with the SMA when you go up on site. All right, so what do we do with all of this stuff? So we're working here. This is an SED of M82, which is a starburst galaxy, spanning, the SED here is spanning 5 orders of magnitude in wavelength. M82 starburst galaxy forming lots of O and B stars. And so those will heat the dust, creating a modified black body or gray body, which will peak over in the sort of 100 microns far infrared regime over here, and with a steeply decreasing spectrum as you go into the 3 millimeter wavelengths or so down here. Then it rises up again because the old stars will explode as supernovae, and they produce energetic particles. And that produces synchrotron radiation. And that will have a steeply rising spectrum into the radio, into the centimeters, and into the meters. And then also, the old stars will produce H2 regions, ionizing the gas, and that ionized gas produce a lower level of radiation, Bremsstrahlung, free emission. Okay, so these are the primary kind of continuum processes that we see in the radio regime, spanning a range from meters to millimeters and beyond. All right, so okay, more about the various aspects here. Let's start off with synchrotron. Synchrotron is a non-thermal continuum process, so it's not being produced. It doesn't have a black body-like look to it. It's being created by not by thermal processes, but by energetic particles that have been created from shocks from supernovae or other energetic events, AGNs also. And there are strong magnetic fields that as the particles come along, coming along at closer speed of light, they're being accelerated rapidly and winding around these magnetic fields. Accelerating charges produce radiation. And that radiation, because of the magnetic field, that radiation has a particular direction. So it's polarized, non-thermal radiation. So as you can see here, basically the strength of the radiation, the shape of that curve will depend on the process of the radiation. In particular, it depends on the distribution of energies in the electrons. And the polarization will tell you the shape. It will tell you the direction of the magnetic field. So the geometry of the emitting process. So a classic example, Cygnus A. So there's an AGN down here shooting out jets. So this is sort of in the centimeter to meter wavelength regime can be observed with the VLA. Okay. Now it's non-thermal, so it's very bright as you go to longer wavelengths. It's sort of it's unlike most other forms of radiation. That turns out to be a useful thing because the people who first started radio astronomy, Jansky and Rieber, would not have been able to detect thermal radiation with the telescopes they had. So they were detecting Sag A, the first, well, Sun and Sagittae were the first radio sources. So it's a good thing there's non-thermal radiation. Okay, but let's talk about the thermal processes. Okay, so there's this Bremsstrahlung, free or braking radiation. So it's first seen in particle accelerators when charged particles were slowed down at the end. They produced a lot of radiation, X-rays and so on. So you had to shield, had to produce a lot of shielding in your particle accelerators. The acceleration in a diffuse gas, which is in H2 regions, is more gentle. So we are talking now about diffuse gas with maybe a few particles per meter cubed. Then the typical spacing between particles, electrons and protons, is around centimeters to meters. And the radiation you produce, due to, the curvature of charged particles, so the acceleration, is going to be of order that wavelength of the separation. So again, in the centimeters to meters wavelength. Its spectrum is very flat, and so but it's very weak. So you can see it at all sorts of wavelengths, again, from centimeters until it becomes optically thick. You can see it from centimeters to millimeters, depending on the strength of the H2 region. So here's an example of W49, massive star-forming region, and all the emission here. So O stars are heating up the gas. There's a dense gas producing stronger emission, and more diffuse gas producing more extended emission. Okay, so from the strength of the emission, you can get basically the emission measure, so it's actually the product of the density of electrons and protons. So it's a two-body process, and it depends also on the path length through. But from that, you can backtrack out. If you can resolve it, then you get a path length, assuming spherical symmetry, and therefore you can get the density of density of electrons. And you can convert also to get the mass. From the rate, because the amount of electrons is going to be proportional to the amount of ionization through things like the Strömgren sphere arguments, then you can backtrack from the density squared to the ionization rate, and therefore you can get the number of O stars and therefore star formation rates. Okay, so it's a very important process to get very basic quantities about star forming regions. Another thermal process, and another important one, of course, is solid body emission, just black body emission. So we have dust particles out there. Dust particles, typical sizes in the diffuse interstellar medium are submicrons. As you go to denser clouds, you get into the microns. And as you get to protoplanetary disks, you go well beyond micron emission, to well beyond micron sizes, to millimeter sizes, centimeter sizes, and beyond. But when you have small particles, they will emit radiation in the same way that solids emit radiation, and fundamentally it's due to the movement of charges in the solid, to the thermal process. But because we're looking at particles that are much smaller than the millimeter wavelengths that we're observing, the emission is not, they don't emit efficiently at these relatively long wavelengths compared to their size. So it's a modified black body, so we call it a gray body. And instead of having a sort of a nu squared dependence that you might expect for in the Rayleigh-Jeans limit, it has more of a nu cubed or even nu to the fourth dependence, very steep dependence, depending on the grain size distribution. So looking at the emissivity, you can get, well, the spectral index, you can get the grain properties. Grains may not be spherical, so they will emit in a preferred direction, like it's polarization. They also scatter in the same way with and produce polarization signatures. Yes, the amount of emission is, as a thermal process, is going to be proportional to, in the Rayleigh-Jeans limit, is proportional to the opacity times the temperature times, or is it surface density times the opacity, and you can backtrack that out to mass times the temperature. Okay, so and of course, the classic example is with ALMA now, we get to just tens of milliarc seconds, and so you can get this beautiful images now of the dust in protoplanetary disks, and learn all sorts of things about planet formation and so on and so forth. And I imagine there's a number of people here who are interested in that. Okay, so this is a key area for the SMA also. Okay, that steep index is also important for extragalactic work because as you look at this, say, M82, that starburst galaxy. There's those different, if you remember, there's those different features. There's a gray body with a very steep spectrum. Then there was synchrotron steep in the other way. and then there was this low-level bremsstrahlung. So if we were to look at that, and stop it here. Oops. Let's see if I can get this to work. Okay. All right. So here is this is now wavelength. So the other one was frequency. So this is your in the optical infrared. You've got your starlight, and then you've got this dust. Black gray body coming in here with some dust features, silicates, and so on and so forth. This is your synchrotron over in the long wavelengths in the radio regime. And in the millimeter regime, we're in this steep part of the gray body. I've stopped it perfectly right here, where at 1 millimeter wavelength, it's at 1 millijansky for this case. Now, as we go to higher redshift, it's all going to shift over to it's going to shift this way to longer wavelengths, and it's going to get fainter, right? And so it's going to shift this way and down. But because you're on this steep curve, you have this sort of magical effect that the flux stays constant, independent of redshift, which is really a remarkable thing. It's a real power of millimeter astronomy to study the high redshift universe, starburst galaxies, star-forming regions in the high redshift universe, because basically you're independent of redshift. You can look in a flux-limited way and get a census that's independent of redshift. Okay, and then eventually things will drop out. Okay, so you have dropouts in the optical. Eventually, they don't drop out in the millimeter to get extremely high redshift. If you were to go to 3 millimeters or beyond, it's fainter, but you can even see yet higher redshifts. Okay, but it doesn't work at any other wavelength. I'll show it one more time because it's sort of fun. You can try to say, okay, let's work at 10 microns. Forget it, you can't see anything now. Let's work at 10 centimeters. It's just going, it's just plummeting, right? It's just this magic place right here. All right, so that's very cool. I'm sure, I know many of you are interested in extragalactic work, but that's a major reason for studying, for working in the millimeter. And another major reason, of course, is that there's all sorts of lines, rotational lines from molecules, have characteristic energies that lay in the millimeter regime. Also, of course, the first spectral line, well, not first, so another major spectral line in the centimeters is the 21 centimeter line from spin flip in hydrogen. But the submillimeter regime, the millimeter submillimeter regime, is particularly rich in lines, and they're created by molecules, asymmetric molecules such as CO. H2 does not emit because it's symmetric. So quantum mechanically, when it flips like that, it looks the same. So there's no change there, and there's no radiation. But CO, when it flips around, it's basically, you can think of it as a center of mass being different from the center of charge. And so as it rotates, that center of charge is rotating. And again, accelerating charge produces emission. It's quantized because we're looking at quantum processes, so we're looking at small things, molecules. And there's all sorts of molecules you can find if you look in the right area. So here's a spectrum of Orion Kea, and just a really dense region. And if you look at some regions, you can barely see the continuum because there's so many lines. What can you do with this? Well, once you have spectral lines, you can really do all sorts of physics, of course. So you can look at the excitation and backtrack to density and temperature. You can look at the molecules and get composition and do astrochemistry. You can measure motions from the Doppler effect, and then there are other effects like by looking at the magnetic interaction between the electrons and the protons. You can back out and get from the Zeeman effect, get the magnetic field strength. Okay, so that's a very rich area, of course. And the submillimeter regime, millimeter submillimeter regime, is extremely rich. So there are many molecules now known. This is an old slide, actually. I think it's up to about 150 or plus. Maybe people know better. Mostly very simple molecules, mostly organics, HC, NO, and so on and so forth. But some interesting ones, and sulfur too, and then some interesting ones, fluorides, and so on and so forth, which are also, opening up all sorts of more knowledge about the chemistry and processes. And I know that there's many people here who are interested in that too, and the SMA can play a big role there because the SMA has a very broad bandpass. And it doesn't average to get you average to get the continuum, but you actually have access to the full bandwidth at high resolution. So you have very high spectral resolution across a very large bandpass. which is actually unique. And, well, at least it's not something that ALMA can do. So it is an advantage here for the SMA. Okay. So that's a very brief intro to the science. I'm going to sort of introduce now various aspects that the lecturers will discuss as we move on through the next couple of days. So here's our SMA antenna. It probably looks like this right now with snow and ice all over it. But basically, it's a 6-meter dish, steerable, parabolic. Radiation comes in through the Cassegrain focus down here. And then through waveguides, it's sent down into a feed horn where it will go into a mixer with the local oscillator, so you can tune it, and you down convert the radiation from hundreds of gigahertz to a few gigahertz, where you can amplify it, and we can do the digitization and all the work that was done, like I say, back with the legacy of centimeter wavelength astronomy. So this sort of thing. You'll hear lots of talks about the antenna, I think by RAM, and all the smart electrical engineers here will tell us about the mixers and receivers and cryostats and all of that stuff. And I think you'll have tours and so on and so forth. This is the area that I know nothing about, so I'm looking forward to those talks. Okay, what do we? So that's the heavy stuff going on. But if we go back to the science and say, well, okay, what are we actually measuring? Then we've got our source, it's emitting radiation, and we've got our antenna and all the back end here. What we are doing, we have a finite resolution on our source. So we measure our radiation over some area, an angular area, delta omega, d omega, and we collect it with an aperture A, and we also filter it through with our spectrometer over some bandpass d nu to measure a power dp. And it's all put in differential form here because the point is there's a characteristic of the source, I nu, here, where we can imagine if we make these small enough, I nu is constant. So there's some property of the source. I'm going to say I have fine enough resolution that it's the same over that source, and it doesn't, and it's a small enough frequency separation that it doesn't change. We'll say that we're just going to measure over a small enough area. If we do that, then the power is basically can be written as this radiation from the source, and it's going to be proportional then. So by doing this, you can see if I doubled the area, I would double the amount of power I get. If I double my bandwidth, if I knew is not varying with bandwidth, then I will get this double the power. Same with the solid angle, right? As long as the source is not changing, if I double the area over which I see it, I'll double my power. Okay, so that's fundamentally what we measure, and it's in watts or ergs per second, if you like CGS. Okay, so the source has we have some finite resolution of the source. We collect it in dA. It goes into the back end. This is the local oscillator, which is, they said, is where the receiver basically mixes with our user-specified frequency. This is how we tune it. Goes into the mixer and amplified and so on. So this will all be lots of discussion down the line. But I want to kind of point out the diplexer here, because this will come in just a little bit. All right, so we measure in watts. So just as a note on units, we don't like magnitudes, right? We're real astronomers. No, it's so we're not using magnitudes. We're using watts, and that I nu is of course a specific intensity, and we're measuring power in watts, but that was power per unit area, per unit solid angle, per unit frequency. So units of specific intensity, watts per meter squared per steradian per hertz. You can think of it as a brightness, and it's fundamental to the source. So this is, if we can measure this, we can learn about what is emitting in the source, right? That's the critical thing, right? Is it thermal bremsstrahlung? Is it dust, right? Is it synchrotron? What kind of spectral line is this, right? That's all those things I talked about. So that's what we really want to get at, okay? It's independent source distance, right? It's a brightness. So that's what we want. This is actually what the most direct observable is actually the integral of I nu over the solid angle, right? So we don't know what's going on when on scales smaller than our resolution element. So we actually measure I nu d omega, the integral of I nu d omega. So that's the flux density, and so the units are watts per meter squared per hertz, or if you like CGS, ergs per second centimeter squared per hertz. And in these SI units, watts per meter squared per hertz is 10 to the 26 Janskis. Okay, so that's our fundamental unit. Okay, so the flux density is what we actually measure, and that will decline with the inverse square law, unlike the specific intensity, because d omega is basically the area divided by d squared. Okay, so that's our flux density. You'll also see that people will use brightness temperature. They'll talk about brightness temperature, especially in the centimeter regime, where if you imagine a black body, B nu, that looks like 2 kT over lambda squared. For h nu much less than kT. That's the Redi-Jeans limit. We still use that as we move into higher frequencies and colder regions. So we break away from the Redi-Jeans regime, but we will still use the brightness temperature for sort of historical reasons, but also because physically it helps us understand what is the temperature what would the temperature of a black body be to produce the radiation that we see. So it's actually a very useful physical unit, especially when you correct for the non-Redi-Jeans, for the Redi-Jeans correction. Okay, so we'll see these three things. So specific intensity, flux density, and brightness temperature. Okay, again, feel free, if any of this is, feel free to ask me questions now or afterwards, whenever. All right, remember that diplexer. So the first stage of the back end was that we would send the radiation down and we'd mix it with a local oscillator. When we do that, that mixing will mean that we can only transmit one polarization through, because we're going to mix it through. And so and that means that and this diagram here is to illustrate the same thing for an antenna. Even without mixing, if you just have an antenna, a dipole antenna, then you will only measure one particular polarization in the wavelength. Okay, so if you want to, so that means if you want to look at, if your radiation is polarized, or even if it's not polarized, we have to take into account you already measure one polarization. If you want to measure polarization, you need two antennas, or you need two receivers. And Ram will talk a lot more about this. Here's a circularly polarized wave, so it's got components in both directions, and so you could measure it with two orthogonally oriented antennas or two orthogonally oriented receivers with diplexers in different directions, and you can measure the polarization. In this case, circularly polarized, but if you imagine any other kind of even a linear polarized line, it would have a component in the two ways, and you could backtrack from that to get the angle of polarization and this degree of polarization. Okay, so that's a very brief introduction to the radiation. Now, why are we here doing for an interferometry school? Well, of course, I think you all know this, right? We're limited in resolution, and astronomy is driven by technology and the need to always get, theoreticians do great work, but really we're empirically driven. We want to see what the objects look like. So we need better sensitivity and we need better resolution. And we want to broaden the wavelength regime, right? So that's how we advance our field. And to get to better resolution at these long wavelengths, we need a big dish, right? So JCMT is the biggest dish on the top of Mauna Kea. It's 15 meters. It's 50% bigger than Keck. I like to tell my optical friends that. But we're operating at a millimeter wavelength, and so the resolution is 14 arcseconds. And Steve Mez is going to talk about JCMT. It's doing great stuff. So venerable old telescope is really kind of getting rejuvenated. It's doing great stuff. If you want to look at 14 arcsecond resolution stuff, and there's a lot of things you can do there. But if you want to get to sub-arcsecond resolution, you need a bigger dish. All right, so let's build a bigger dish. Let's build the GBT. That's 7 times bigger than JCMT. So it's 100 meters across. Unfortunately, it only observes at 7 times the wavelength. So lambda over d is the same. So the resolution, the GBT is roughly 14 arcseconds at its shortest operating wavelength. This is a big dish, right? This is, in fact, the largest steerable structure in the world. So that's great. There was a bigger steerable structure, but it broke. It's very hard to build these things. Actually, this is a very interesting website. If you're interested in the background to this, this was built before finite element analysis and so on, and so they did what they could, but there was engineering problems with it that they didn't figure it out. And yes.
I think there's a conspiracy. There was somebody from Effelsberg there that day.
There is, yes, you can find all sorts of stuff on the web. All right, so
I also believe that the last observation was a SETI observation.
very suspicious. Lots of things to talk about over beers tonight. Okay. So, if we want to build really big things, maybe we can fix it, like Arecibo, or the FAST telescope has just started work in China. So this is the biggest radio telescope. It's 500 meters across, fixed in the ground with a spherical aperture. So you can, now you move your secondary around to look at things. 500 meters across, that's really huge, but its shortest operating wavelength is a meter, and that's with an adaptive surface. So its resolution is 7 arc minutes. So, so you're not going to resolve a protoplanetary disk with that. Lots of great science you can do with it, enormous sensitivity. But of course, to get to the really high resolution, if you want to get to sub-arc second resolution, 1 millimeters, you've got to get to baseline, or you've got to build a telescope 200 meters across that's accurate. So how do you get that accuracy? Well, what you do is you use the Earth as your stability, and you create a number of antennas, and you connect them together. So the strength of the stability is that you have well-designed small antennas that have good surfaces, and you rely on the Earth not to move, though VLBI will talk about that too, I think. And you synthesize the signals. Okay, sounds easy. There's a lot of work behind that, right? You'll see a lot of the mathematics, the elegant mathematics that go into that in the next few lectures, and you'll see about all the amazing electronics and that go into making that actually happen. The key, though, is, as I said at the start, is that in radio, we are looking at, we measure the electric field, so we measure amplitude and phase. And so and we can digitize it because we have all this great technology that you have in your pocket, right? We're downgrading our signal to the same kind of frequencies where you have this wonderful electronics, cheap electronics, fast electronics. So we can measure amplitude and phase, we can digitize it, we can record it, we can Fourier transform it, and so on and so forth, and do all the mathematics. So this is the key. This is why we can do interferometry, why it's much easier to do in the radio than in the optical infrared, and it's why we can achieve the best resolution then of any wavelength in the radio and open up this all sorts of science that I talked about. Okay, so this was pioneered by Martin Ryle in 1974. It's probably noteworthy, I'm sure you'll know this, but this is the 3 Mile array in Cambridge, England. As I said, you could do this from the ground, it's centimeter wavelengths and beyond. This is the first Nobel in astronomy, it's worth noting. And another point that I like to tell my students is he got the idea from this from going to a lecture by Bragg. You'll probably know from high school stuff how if you shine X-rays at crystals, they bounce off different layers and they interfere with each other. And from the photograph, as you look at the photograph of that on the backside, you can infer the structure of the crystal from the interferometry pattern. That's basically what we're doing here. And it was from going to that lecture that he had this idea. So I tell my students it's always important to kind of keep an open mind. Don't just say, well, that talk's not in my field, I don't care about it. You get inspiration from all sorts of areas, and especially when there's Nobel Prize winners talking. But anyway, so keep an open mind as you move forward with your both with your science and work throughout your PhD and postdocs and so on, but also for the rest of the lecture, right? So if there's talks about the correlator or something, you say, I don't care about that, I'm not an electrical engineer. Or there's talks about science, you say, I don't care about that because I am an electrical engineer. Don't, listen to everything because there's a lot of stuff you can get out. So that's all I have to say. So enjoy the school, and thanks for your attention. Okay.